In Week 2, we are still looking at the context of large systems. The lecture this week addresses two major themes. Just what is a large system, and why is it so hard to develop one? What makes a system large? Let's look at some typical values. Certainly the number of lines of source code is one measure. Most cost estimation models use source code size as the primary factor in determining cost and schedule. Then again, we can look at the complexity of the environment. How many other systems, including humans, will the system need to intelligently deal with? How about the actual development team? Both the number of independent suppliers and the depth of the supplier chain represent a measure of largeness, certainly with respect to buildability. And of course, nothing is totally independent of everything else. So when you add up all the developers, suppliers, testers, installers, maintainers, writers, and support personnel, not to mention success-critical stakeholders, there can be a small army of people that need to be coordinated with respect to activities, information, specifications, technology, internal and external changes, and just about every possible dimension you can imagine. All that coordination means the project's primary personnel may spend more than their normal allotted work time in meetings with no tangible outcomes. By the way, where did that 40-hour week we were promised go? Okay. So the inherent largeness of systems and the development organizations is pretty confusing. But what about all those trends we talked about in the first week? How do they impact size of systems? Systems of systems and network-centric services are terms that are used more and more when describing large systems. And that makes sense, since every system that is added into the systems of systems probably enlarges the code base. Although, if you think about it, one person's system of systems could easily be someone else's system. Think airplane engine control is part of airplane engine, is part of airplane propulsion, is part of airplane, is part of air transportation system, or in the words of Augustus de Morgan, a Victorian mathematician, great fleas have little fleas upon their backs to bite 'em, and little fleas have lesser fleas, and so ad infinitum, and the great fleas themselves in turn have greater fleas to go on, while these again have greater still, and so on. We continue to ask systems to be more flexible in how they communicate and even how they function. Remember the autonomous systems concept from last week. An embarrassing complicating factor, though, is that we are rarely, if ever, afforded the chance to build a large system that is just like something we have already built. Every large system has to do more, do it faster, with more safety and security, and of course, cost less. Right. We are always reaching farther out into what is possible, and so the very unprecedentedness of many systems increases their intellectual, if not their actual size. Admittedly, nothing seems to remain stable anymore, but we must also face the idea that when these very large systems grow, unexpected behavior will emerge as well. In Robert Heinlein's The Moon is a Harsh Mistress, the idea of a computer system that ends up with so many parts and sensors that it becomes sentient is the basis for the book. Not sure this is really a problem. This whole concept of emergence, though, is tricky. What is emergence and what is requirements creep? Or is there really such a thing as requirements creep anymore? Now, to the actual effort required to build these large systems. Truthfully, most systems of any consequence aren't really programmed from the ground up. They're really integrated from various numbers of new and old components. IBM and other IT organizations now refer to brownfield systems as being the rule rather than the exception. Commercial and government off-the-shelf software, as well as legacy systems, are all involved in this concept. Some large systems aren't really built at all. They are simply a customized, parameterized, adopted, and otherwise change-inflicted version of a larger core system that already exists. But, you may ask, if these software systems are so hard and so likely to fail, why build, or attempt to build, them at all? Well, there are real needs that only large systems can meet. For example, to bridge the gaps between a number of independently developed systems, it may require that a whole new system be built that handles not only the existing functionality, but also some of those emergent properties we talked about. weapons systems, and their equivalent in the commercial market all need to interact and interoperate to achieve their mission. It is the large quantity of software that makes this even feasible. Let's look at the characteristics of these complex systems and how software enables them. Being composed of component systems is a hard job for something in hardware, but a breeze, comparatively, for software. Rapid change of functionality or mission parameters is also clearly easier in software. And if you need to field interim or incremental functionality, software is definitely the way to go. Think about fielding an airplane that had a fuselage and engines, but the wings were scheduled for the next release. Here's a good summary of the benefits and risks. Take a look at them. Of course, with every benefit comes risks, large and small. And then there are those compound risks where the sum of the parts is more deadly to the program than any one of them singly. Let's look at a few large software systems. In some ways, these are the first of a new breed of systems that the Software Engineering Institute at Carnegie Mellon University and the Army have identified as not just large-scale systems, but ultra-large-scale systems. In their Ultra-Large Systems report, SEI presents an interesting view on this concept. The following is my take on their material, so apologies to Linda Northrup and all the other ULS authors if I misrepresent them. First, let's define an ultra-large-scale system. In general, ULS systems are, or will be, interdependent webs of software-intensive systems, people, policies, cultures, and economics. In short, they are systems of systems at Internet scale. And, as we saw in large systems, scale changes pretty much everything. Suddenly, we are in an environment where the little control there may be is decentralized, and the requirements are out of the designer's hands, which means they can be conflicting, unknowable, diverse, continuously evolving, and generally chaotic. The ULS is made up of heterogeneous, inconsistent, and changing elements. They are most likely cyber-physical connections, and the boundary between humans, machines, and the environment erode. Failures are expected and essentially represent the normal state of affairs. Now, some of these characteristics do exist, often as anomalies in today's systems, but in ULS systems they will be the standard way of doing business. Stop for a second and consider what this means to the foundations of architecture, design, acquisition, development, and governance. None of our current approaches makes any sense in such an environment. Imagine trying to fit one of these systems into a traditional systems engineering lifecycle model. As an example, how do you think the critical design review would be handled without requirements, schedules, or any of the other subjects usually handled in the traditional death-by-PowerPoint activities among 300 or 400 of your closest friends? We currently approach systems in one of two ways: top-down, hierarchical, plan-driven, with centrally controlled activities and some inherent verification and validation activities, or in an agile, fast-cycle, frequent delivery, no design outlives the product manner, with small teams and tacit knowledge. Since neither of those makes any sense, it is necessary for us to come up with a new perspective. Henry Petrosky describes this situation very well when he says, "The older is not always a reliable model for the newer, the smaller for the larger, or the simpler for the more complex. Making something greater than any existing thing necessarily involves going beyond experience." Mary Shaw from the Computer Science Department at Carnegie Mellon University, one of the authors of the SEI study, came up with a brilliant metaphor for the necessary adjustment. Today, she said, we build buildings. We need to think about building cities. Another way to consider it is, rather than creating independent individual system users species, we need to think of a whole socio-technical ecosystem. Obviously, ultra-large-scale systems present us with a number of extremely significant challenges.